Welcome to today's Explainer. We're jumping right into a piece of technology that is absolutely foundational to our modern lives, yet it's completely hidden from view. Today, we're unpacking the literal backbone of modern communication networks. Because whether you're controlling a massive industrial system, managing a complex railway, or honestly just streaming high-definition video across the globe, there's a very real physical infrastructure making that all possible.
It's a question we rarely stop to ask, isn't it? We live in this world where communication just feels like magic. We send a message, and boom, it instantly appears on the other side of the planet. It feels totally wireless, effortless, and invisible. But we need to look past that illusion of magic today, because the actual physical reality of how we transmit data at the speed of light is so much more fascinating than fiction. It involves highly engineered physical materials laid out across the ocean floor and buried right beneath our feet.
Okay, let's dive into this. Here is our agenda for today. 1. Introduction to fiber optics. 2. How light transmits data. 3. High-speed transmission rates. 4. Installation constraints and fragility. And finally, 5. Precision repair and maintenance.
Starting with Section 1, Introduction to Fiber Optics. Let's ground ourselves right at the very beginning with exactly what we're talking about when we discuss the physical infrastructure of the digital age.
Now, at its core, a fiber optic cable isn't made of some complex microchip or an elaborate electronic circuit. It's a telecommunications cable featuring a perfectly pure, incredibly thin glass core designed specifically to transmit digital data using short wavelength laser light pulses. That's it. Its one and only job is to provide a flawless, crystal clear highway for light to travel through. It is literally just extremely pure glass carrying light. Moving right along to Section 2, how light transmits data. So we know we have this glass core, but how exactly does that light travel, and more importantly, how does it carry our information?
Well, the data isn't sent as one steady, continuous beam. It's actually transmitted as incredibly fast pulses. What's really interesting here is how engineers choose very specific invisible wavelengths for this job. For long-distance transmission, we use what's called single-mode fiber, operating at a 1310 nanometer wavelength. That provides improved bandwidth and far less signal loss over vast distances. But for short-haul tasks, say connecting servers within a single building, multi-mode fiber at 850 nanometers does the trick. Together, these specific setups act as the bare infrastructure. They are the absolute bedrock upon which all of our digital transmission systems are built.
To really put this into perspective, think about the environment of a real-time control system. Whether it's running a massive railway network, a national power grid, or a global data hub, the seamless, safe operation of these critical environments depends entirely on the continuous flow of those tiny laser light pulses. Operators are making real-time, high-stakes decisions based on data that is literally flashing through microscopic glass threads beneath the ground.
All right, Section 3, high-speed transmission rates. You might be wondering, why do we go through all the trouble of ripping up old communication systems just to lay down glass? The answer is pure, unadulterated speed.
We are talking about rates of over 100 gigabits per second. Just let that number sink in for a second. To put that into perspective, that is the equivalent of downloading dozens of full 4K movies in the exact time it takes you to blink your eyes. Because light operates at such a tremendously high frequency, it offers a staggering transmission capacity that older, traditional methods couldn't even dream of hitting. This is the exact rate that makes instant global video calls, huge cloud computing networks, and massive data transfers our daily reality. And this brilliantly illustrates the real revolution here. When we compare fiber directly to the older standard, copper multi-pair cables, the difference is night and day. Copper is bulky, it's heavy, and it's fundamentally susceptible to electromagnetic interference. If you run a copper cable anywhere near a high-voltage power line, your signal gets completely scrambled unless you use incredibly heavy, expensive protective shielding. Fiber, on the other hand, it's small, it's incredibly lightweight, and because it uses light instead of electricity, it is completely immune to electrical noise. You could literally wrap a fiber optic cable around a massive industrial power generator, and the data pulses inside wouldn't even flinch.
Which brings us to Section 4, installation constraints and fragility. Now, let's take a slightly more grounded, cautionary look at the physical limitations we face with this technology.
Despite its incredible speed and its perfect immunity to electrical noise, we can never forget the fundamental nature of the material we're working with here. Glass has its limits. It is a highly fragile material. Treating it like a rugged, old-school electrical wire, bending it, yanking it, or crushing it will absolutely shatter the core and result in total system failure. This means during design and installation, incredible care has to be taken.
Engineers have to follow strict bending radius constraints. Think of the light pulse traveling through that glass core kind of like a high-speed race car. As long as the track curves gently, the car stays on the road, bouncing safely off the walls through a physics principle called internal reflection. But if you try to force that race car to take a hairpin turn, the physics completely break down. Bending the cable too tightly causes the internal reflection to fail. The light simply escapes right through the side of the glass core, resulting in immediate, total data loss.
Finally, let's look at Section 5, Precision Repair and Maintenance, because when that glass, buried underground or strung along harsh railway environments, eventually does break, fixing it requires a highly specialized, almost surgical approach out in the field.
If a construction excavator accidentally snaps an old copper wire, a technician can basically just strip the ends, twist them together, slap on some electrical tape, and call it a day. But you absolutely cannot duct tape a fiber optic cable. Repairing these glass threads requires entirely specialized, incredibly expensive equipment to perform what is essentially microscopic welding, very often while standing in a cold, muddy ditch.
So, the crucial point here is understanding how this extreme precision repair is actually pulled off. First, to even find an invisible break in a cable that might be miles and miles long, technicians use a device called an OTDR, an optical time domain reflectometer. They fire a pulse of light down the fiber, and when it hits a fracture, it reflects back. By timing that exact reflection, the OTDR pinpoints precisely where the break is located. Next, they have to prepare the damaged ends by making a perfectly clean, microscopic cut. And finally, they place those two ends into a machine called a fusion splicer. This incredible piece of tech automatically aligns the two microscopic glass cores and then uses a literal electric arc to heat and perfectly weld the glass back together into one single continuous strand. It's an incredibly meticulous process, and I think it perfectly highlights a fascinating duality. We're sending immense, mind-boggling volumes of data across the world, in the literal blink of an eye. Yet all of it relies entirely on microscopic threads of glass that could be snapped by a single misguided shovel. It leaves us with a pretty critical question to ponder as we wrap up today. When the very backbone of our digital world, the infrastructure that holds all of our modern communication together, is fundamentally made of fragile glass, how do we engineer the future of resilience? Thanks for joining today's Explainer, and we'll see you next time.